All right, are you ready to practice? We are going to translate from ordinary language into propositional logic notation. We are going to create truth tables for statements, and we will also practice with, in that vein, with determining sub-operator and simple statement values when we have truth values assigned. And then lastly, we will practice with creating truth tables for arguments. So let's get started. All right, first, our very favorite magic pen. First, recall that you have a couple of ways that you can approach translations. You can identify your simple statements first. You can identify your connectives first. It doesn't really matter which. We'll go back and forth. And then think about what the connective is doing once you've identified it. And what I mean by that is, for example, is the connective here rejecting the conjunction? And the short answer is yes. So we're going to have a not, and then both goes together. I'll just put it here. Here is, or I'm sorry, I said both goes together. I meant to say both the simple sentences that are conjoined go together. Okay. So we'll bring down our negation, our parentheses, and our dot. And now we have two simple statements. Maple tree leaves change color in the fall, and I'll just use M for maple. Tree leaves change color in the fall. And P for pine tree leaves change color in the fall. Now, remember a couple things. One is that your negation, which is symbolized by the tilde, always goes to the left of whatever it's negating. And since it's negating the both, it's saying no to the dot. So we need to have a pair of parentheses around this conjunction sentence so that we know what's being negated. Another way to think about it is that the parentheses tell us that M dot P acts as a unit. And then the other point to remember is that all of our operators, with the exception of tilde, is always like the white stuff in an Oreo cookie or the stuff between the bread in a sandwich, right? You always have your connective symbolized by an operator, dot, disjunction, conditional, biconditional, sandwiched between two sentences. Okay, next one. This time, let's find our simple sentences. So we have cacti, leaves change color in the fall. Notice how I sort of stumbled as I'm looking at what I'm given. I ignore the conjunction, I ignore the negation. So I have C for cacti, leaves change color in the fall. And then I'll use S for succulent leaves change color in the fall. Now notice what we're being told. We're being told that both do not. So we say both do not. Now, why am I not putting the negation in front of a parenthetical like I did up front? Well, or sorry, like I did in the first sentence. The first sentence says not both. This says both not, which means this one not and this one not. You might find that a more intuitive version of the sentence is the logically equivalent neither. Okay, so the four dots signify logical equivalence. It's not the case that either one does. Both do not. Okay, next we have the Toyota is going to park in this space if the Honda doesn't. So I hope that it's clear that this is an if-then sentence. Remember our tips, and I'll put them up here. So the standard translation is whatever comes after the if goes on the left side of the horseshoe, and whatever comes after the then goes on the right side of horseshoe. We have one exception, remember, and that's only if. And only if expresses a necessary condition, and the necessary condition always goes in the consequent position. So sufficient condition on the left, necessary condition on the right. So we've got an if-then sentence, so I'm going to circle the if. If the Honda does not, so if not the case H, then the Toyota. Now, we don't have anything compounding the sentence, the Toyota is going to park in this space, independently of the rest of the sentence, so it's just capital T. Here we have an example of an only if. So only if is an expression that reflects necessity or exclusivity. Do you remember only if or only from categorical logic? And when we translated only in categorical logic, we translated whatever comes after only in the predicate position. And if you think about how we took conditional claims from chapter 5, section I, as being translated as universals. So if this, then that became all this are that. If we had only if, we translated whatever came after only if in the predicate position. So here the predicate position is the right side of horseshoe. Okay, so an automobile is a sedan, so I'll use S for sedan, only if it carries up to 4 people. And I'm just arbitrarily choosing F for carries up to 4 people. Now remember, if we were working in an argument, anytime we had the sentence, it carries up to 4 people, we'd need to use F. Similarly, in terms of consistency of notation, if you have, let's say, a subject named twice, right? So something like, Alice does laundry and washes her hair. You're not going to use A for Alice does laundry, Alice washes her hair, because we won't know which A refers to doing laundry, which A refers to washing hair. So we need to pick different letters. Okay, next. Passing philosophy 6 is a sufficient condition for completing the critical thinking requirement in the GE curriculum. So the language that should jump out at us here is sufficient condition. Remember that the stuff that is the sufficient condition goes on the left side of the horseshoe. So passing philosophy 6 is a sufficient condition for completing the critical thinking requirement in the GE curriculum. It is necessary, so a necessary condition for graduating is completing a critical thinking course. So remember, the necessary condition always goes on the right side of horseshoe. And I use C for completing a critical thinking course, and then G to graduate. So the way that you could read back this sentence is, if you graduate, then you must have completed a critical thinking course. Neither Diet Coke nor Pepsi contains sugar. So remember, as we had earlier, the not both, we had a negation of the conjunction. Here we have a not either. So it's not the case that one thing or the other. So we could say Diet Coke or Diet Pepsi. Now, for those of you who are more comfortable with this translation that I'm about to write, you'll see that your intuitions are perfectly legit. So these two translations, these two propositional logic notation sentences, statements are logically equivalent, not either, both are not. Then we have Cleo is either not at the library or not at the cafe. So we have Cleo at the library, Cleo at the cafe. Cleo is either not at the library or not at the cafe. This expression is logically equivalent to not both. She's either not here or not there. We don't know which one she's not at, which is equivalent to saying it's not both the case that she's at the library and at the cafe. So remember, we've got Cleo at the library, Cleo at the cafe, right? Those are our two simple sentences. So we have cafe and library. Then we have our connectives. And one of the reasons why, if you get the phrase either or, you get the phrase if then, you get the phrase both and, that I will link them is so that we know we're talking about a single connective. All right, next, being 20 years old is neither a necessary nor a sufficient condition for being a college student. Now, this is pretty complicated. Let's break this down. All right, first, let's talk about our simple sentences. We've got being 20 years old, and then we have being a college student. So we could say C for a college student, T for 20 years old. Now, notice that we've got a not either, right? So let's just go ahead and throw into a pair of parentheses governed by a negation the disjunction, so that we know we've got that. And then notice also we've got necessary sufficient. So we've got to deal with the T horseshoe, C horseshoe, T relationship. So let's start with what would happen if we didn't have the neither. So suppose we said being 20 years old is a necessary condition for being a college student. We would then say C horseshoe T. Being 20 years old is a sufficient condition for being a college student. So we have, I'm going to put it over to the left because I realize that I've kind of run out of room here. Being 20 years old is a sufficient condition for being a college student. Now these I put in parentheses. Okay, so now we're ready to reject that this is the case. It's not the case that this or this. Now, what we could do, but it would make it a little bit more visually complicated, is push that negation through, right? And we'd end up with this sentence, if this is more intuitive for you. It's not the case that T is sufficient for C, and it's not the case that C is sufficient for T. I hope I said it's not the case that T is sufficient for C, and it's not the case that C is sufficient for T. Another way to say it is, it's not the case that C is necessary, and it's not the case that T is necessary. All right, next, a flower is both beautiful and fragrant, or it's neither. Now, this is not actually the case, right? There are plenty of, arguably plenty of beautiful flowers that are not fragrant and fragrant flowers that are arguably not beautiful, but that's not our concern, right? So we have a flower that is beautiful, a flower that is fragrant. So let's do B, capital F. So what we're saying is B, it's both B and F, or it's neither B or F, right? So neither is negation, parentheses, disjunction in the middle, right? And then we have our conjunction. So we have B dot F or neither B or F. Next, let's move on to truth tables. Before we do so, let's remind ourselves of our definitions and some shorthand ways we can remember them. So, for example, we know that the dot is true, the disjunction is false, the conditional is false, the biconditional, I was going to say bi or triple bar. Biconditional or triple bar is true if and only if we have the following conditions. Each of the conjuncts is true. Each of the disjuncts is false. The antecedent is true and the consequent is false. And lastly, the truth values are equivalent. So you can maybe jot this down and use this as a handy reference. I hope it's obvious that your negation, of course, is always going to be the opposite of whatever the original value is. So we have true and false. Okay, so there's a handout with this sort of cheat sheet on it that you might want to have at your side as you're practicing. But let's go ahead and move on. Now, one of the ways you can approach your truth table is to put your values directly underneath your simple statements. Alternatively, you can do what Baronet does, and that is have reference columns off to the side. It really doesn't matter. I go back and forth. What you do need to remember, though, is the formula for determining how many rows or lines your truth table is going to have. So the number of lines or rows in the truth table is 2 to the number of simple statements. And so you have here 2 simple statements, so 4 rows. And remember the way that the values lay out. This is just standard for any logic textbook. You have half true for the first and half false. And then you begin to take half of the first set, divide that in half, until you end up with, of course, we do that immediately in the second sentence, until you have alternating TF-TF. So this is just the standard approach. Another way you can think about it is this. A could be true, B could be true. A could be true, B could be false. A could be false, B could be true, and then each could be false. There's no other possible permutation, no other possible set of worlds or possible combinations of truth values. Okay, when you're looking at this sentence, you need to identify which is the main connective. Do you remember how to do that? Well, you know that your main connective is the one that drives the sentence. So the only connective, the only operator, I should say, that actually drives the sentence as a whole is dot. The tilde says no to B. whereas the tilde and the value of A are conjoined in the final determination. So we're going to calculate or determine the tilde first and the dot second. So not true is false. Not false is true. Not true is false. Not false is true. Now we take these values and compare them with A. True dot false is false. True dot true is true. And then wherever you see even one false, the sentence is false. So this sentence is what's known as contingently true, which is to say it is true on at least one row. And once, remember, you've calculated or determined your truth values, you don't need them anymore. What you're looking at is the dot, because this is a conjunction. This is an and sentence. All right, let's continue. Now what I'm going to do, since we've already run through our review of the truth definitions and setting up a truth table, is I'm just going to go ahead and set up the possible values. You can see I'm just going ahead and writing them directly underneath the atomic sentence. This negation covers only A. This negation covers only B. So this horseshoe is the main operator, and that means that I can go left to right, calculate this tilde first, this tilde second, although I could do either one first, it doesn't matter, but I must calculate horseshoe last. So false, false, true, true. I'm done with A. False, true, false, true. I'm done with B. And then let's change up the pen color. Remember, a horseshoe is false in one case only. That's when the antecedent is true and the consequent is false. So here again, we have a contingently true sentence. Now, why, remember why, or let me ask you, why do you remember that we care about churning out these truth tables? Well, we want to know what all of the possible values are. Under what conditions could this sentence be true, and under what conditions could this sentence be false? Because this will factor into this or any other sentence that is equivalent to these values, determining whether or not an argument is valid. More on that in a little bit. All right, next. Remember that whatever's within a parenthetical is never the main connective. So we're going to determine the tilde outside of the parentheses last. And then within the parenthetical, the disjunction, the wedge, is the main connective. It's bringing together A with tilde B. So we have to calculate tilde first. Now this time I'll just go ahead and put the possible values off in a separate reference column. Okay, so we have false, true, false, true. We have true, true, false, true. And then lastly, because we're looking at the values under the disjunction, under the wedge, in order to determine the value of the sentence as a whole, we've got false, false, true, false. Sorry, I thought I changed pen color, but I didn't. False, false, true, false. All right, now we've got a more complicated sentence in two ways. First, can you see that we have 3 simple statements? So that means that we need to generate 8 lines or 8 rows of a truth table. We also have a slew of operators. So what I would like you to do is identify, as I'm setting things up, the main connective. And I'm going to put the values directly below the simple sentences here. 1, 2, 3, 4 true. 1, 2, 3, 4 false. These same values go under A in its other iteration. C is the second one in, so it gets half true, half false. Half of that first set of values, A's values. And then always the last sentence on the right alternates true, false, true, false. Okay, did you identify the main connective as the main operator as horseshoe? I hope so. If we go left to right, we're going to determine dot first. Then we need to determine tilde because it covers only B. So it is the most sub of the sub operators. Then the wedge connects A with tilde. And then the tilde outside the parentheses is what governs this entire second half of the conditional of the horseshoe, and then we do horseshoe last. So let's get to it. Actually, let me change pen colors here. So true, true, false, 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 false. And then I'm going to go back to, I'll keep it red for right now. Or actually, no, I'll make the last, I'll make tilde, the last tilde red. Okay. False, true, false, true, false, true, false, true. Disjunction is going to be all of A's values, disjunction tilde, right? So true, 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 false, true, false, true. And now I'm going to take the values of the disjunction and reject them. So now we're in a position to take the dot and the first tilde and generate the horseshoe truth values. So we know that there's one in one case only when the horseshoe is false. In all other cases, it's true. All right, so assuming there wasn't any typo in there, this sentence has at least 2 instances where it comes out false. So it's not what is known as a tautology, which would be a sentence that always comes out true. And it's also not self-contradictory, which is a sentence that always comes out false. All right, so we know we have 3 simple statements, 8 rows or 8 lines. And remember, you're taking half of your first of your first sentence's values, and using using 2 trues and 2 falses. And then as you get to your last, you're simply alternating. Okay, so the main connective once again is the horseshoe. Within the first, the left side of the horseshoe, We have a negation, which need a tilde, which needs to be determined, the values of which, I should say, need to be determined before we determine the wedges values. And then it really doesn't matter which one of these tildes you do third. One or the other is fine, but you need to do the wedge fourth, the exterior tilde fifth, and your horseshoe sixth. So we are alternating our values because of the definition of the negation, and then taking A and tilde values, and by definition of the disjunction, getting the following. So what I'm going to do to keep things clear, I hope, is box those values up, that column up, and then move on. So we'll have false, 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 true, 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 false, true, false, true, false, true, false, true. Do you remember why? The tilde here is rejecting all of the original values of A, which I had just put under this iteration of A, but you could also plug them in here. And then the negation, the tilde here, is saying no to all of B's values. And then we're going to take the tilde values on each side of wedge in order, and the meaning of the definitions of wedge, in order to determine wedges values. And then lastly, we're going to, not lastly, I'm sorry, I apologize. Second to lastly, we're boxing up this column here under wedge so that we can remember what we're rejecting here. So we've got true, false, true, false, 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 false. And then let's change our color here so that we can be super clear about what we are determining. And we take our definitions. Let's see, I got off track here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's going to be true, false, false, and should be true. Did I get that right? 1, 2, 3, 4, 5, 7, 8. Oh, whoopsie. A little extra there, huh? Okay, but we got it. I tend to, when I don't have lined paper, when I'm at the board or working in an environment like this, my lines go all over the map. So it's not a bad idea to use lined paper. But so here we have our final values. And again, let's just make sure that everything is on board. Everything is accurate. This is where things started to get a little bit wonky for me visually. Aha! I calculated wrongly. That's why it's good to have your rows line up. And then, of course, this one is correct. All right, moving on. Okay, so now we're going to move back and forth between two similar exercises. We're going to either start with simple statement values and build up to the main operator, or we will start with a value of the statement and then work our way back. And both give us good practice with our understandings of truth definitions for operators as well as main operators. So first, we're going to say that A is true and B is false. So we'll plug the values under each iteration. And then we know that neither, or none, I should say, of the operators within the parentheses is a candidate for the main operator. So let's calculate those first, and then we can determine which of these two is the main operator, although I think you already know. Okay, so I'm going to change the pen color, keep things as clear as possible. So we know that this sentence is false. Now, if you are feeling super clever, you are thinking, aha, I already know that dot is the main connective, is the main operator, and I know that dot is false when at least one of the conjuncts is false. So this whole sentence is false. True, but let's pretend like we don't know that. Okay, next, tilde false is true, tilde true is false. We really only need to know that one of the disjuncts is true in order for the disjunct as a whole to be true. And then when we look out here, we see that dot is the only connective that's bringing together two statements, whereas what this tilde governs is all inside of this parenthetical. This tilde doesn't govern this sentence. So we end up with the following. So negation, true is false. And then, as you've already found, the dot is false. So this is one of the rows on a 4-row truth table. But what we're doing here is just arbitrarily picking values and seeing what we get. Now, let's start with the value of the compound statement, which is a dot statement, and work our way back to, as much as we can, the simple statements. So we know that if dot is true, that means that the disjunction must be true. And if dot is true, that means that the triple bar is true. Now, we also know that the tilde, the first tilde and the second tilde are not the main, are not candidates for the main operator on the right side of dot, because it's the triple bar that's holding together these two sides. And we certainly know that we could have tilde as a main operator. We just haven't had it as yet. Okay, so let's go back over to the disjunction. We know that the disjunction can be true in 3 ways, right? Each could be true. One could be true, the other could be false, or the other could be true and the one could be false. So it seems like there are a lot of options here. What about the triple bar? There are 2 ways for triple bar to be true. And that's if both are true, the tildes are true, or both tildes are false. Now, suppose that we said that tilde was false for the negation here, for the, for the left side of the triple bar. Then that would make A true, and then we could plug that value in here, and it wouldn't matter what C is. And if we made tilde false here, that would make B true. But we wouldn't really need to know those values. So really all we can get, knowing that the dot is true, is that the wedge is true and the triple bar is true, but there are 3 ways for the wedge to be true, and there are 2 ways for the triple bar to be true, and we're not forced into a value for each. What if we say that in this case the dot is false. Well, here what's tricky is that there are three ways for dot to be false, right? We could say that the left side is true, the right side is false, the left side is false, the right side is true, and each is false. So the tricky part is we don't know what that's going to be. We also can say that if the dot is false and this triple bar is true and this triple bar is false, then that means that we're going to have to come up with different values. But notice that we've got A, C, and tilde A, tilde C. So what if instead we make both of these false? Then we could have A be true arbitrarily and C be false, and that would get us a false triple bar. That would make tilde false and tilde covering C true, and that would make triple bar false. But again, this is just conjecture, because when dot is false and its sub operator can be false in two ways, and no other part of the sentence is forcing us into making A true or C true or A false and C false, we're left with sort of an open-ended set of values. All right, now let's move on to, once again, plugging in values. So A is true, C is true, and B is false. Next, let's determine what the main operator is. Notice this pair of brackets tells us that this entire animal is the left side of a triple bar, C is the right side. So that means triple bar is the main operator, and then the sub operator is this tilde. So we have to take, we don't have to do any calculating here with C, but we do know that if this triple bar is going to come out to be true, then we need to have this tilde come out true. But let's see what we get. So I'll move right to left because we know that within this parenthetical is not the main sub operator, and within this parenthetical is not the main sub operator. We're going to get to this dot second to last. So basically what we have to do, the order that we have to take is this. We could do either left to right, we could do horseshoe first, or right to left, we could do the tildes first, second horseshoe second, tilde third, and then dot fourth, and then negate the dot. Okay, so tilde F is true. Whatever A is, the horseshoe comes out true because the consequent is true. But let's go ahead and complete this. So then we get false, horseshoe true is true. Then tilde false is false, which is going to force dot to be false, right? So whatever horseshoe is, and it does happen to be true, dot still comes out false, and that's because the right side of dot is false, and then tilde false is true. Finally, we take the tilde and C, and we get the value of the sentence as a whole, which is true. All right, so now we have a very similar sentence main operator here is the triple bar. We're told that it's false, and there are two ways it could be false, right? C could be true, C could be false. Since we don't know, we could just pick a value and determine what we get. We also know that this entire sentence in brackets is either going to be true or false, right? So if the tilde is false, then the sentence C has to be true. If tilde is true, then the sentence C has to be false. So what if we just go ahead and arbitrarily plug in some values? What if we said that the tilde here is false? That would make dot true. And for dot to be true, triple bar and tilde would have to be true. And if tilde is true, wedge would have to be false, which would mean that each of the tildes would have to be false, which means that A and B both would have to be true, which would yield a true triple bar. So that could work out quite nicely. But again, remember the fact that we're starting with a false triple bar and there are two ways for the sentence to be false means that in this case we're sort of not forced into, given the other elements in the sentence, we're not forced into saying that one or the other is the one that's true or false. All right, now we have an argument, and I hope it's clear that these two columns are our reference columns. This is a space between, or a slash between, premise 1 and premise 2, and then we have our conclusion, which I'm separating from the premises by 2 slashes. So we have true, true, false, false, true, false, true, false in our reference columns. We are going to determine the values of each of our premises and our conclusion. The second premise will just take the same values as in the reference column for A, and that's because there's no operator acting on it. The tilde denies the dot, so we calculate or determine dot first. And we end up with, and then lastly, the tilde rejects all of the rejects the original value of B. So all of the values end up as follows. All right, so remember what we're doing when we're looking for the argument's status as valid or invalid. We're looking at under the rows under each of these columns. More specifically, we're looking for the rows on which the conclusion is false. If the conclusion is false while the premises are true, then the argument is invalid. But as you can see, that on the two rows, row 1 and 3, where the conclusion is false, at least one of the premises is false. So on row 3, premise 2 is false, and on row 1, premise 1 is false. And one of the great things about constructing truth tables for determining validity is that you really, I hope, get a great sense of what it means to say that an argument is valid. There are no other possible ways for this argument to be in terms of truth values. And so since we've exhausted all possible permutations of truth values and none of them have yielded an invalid argument, the argument is valid. And this will help us as we go to use valid argument forms as rules in proofs. So we can use a valid argument as a rule precisely because the argument never fails. It never fails because all possible values have turned out such that there's no row where the premises are true and the conclusion is false. All right, let's do construct another truth table. I don't know if yellow is good, but we're going to try it. Ugh, actually, it's not good at all. I've never tried it, and now I know why. So we've got our possible values. We know that this is premise number 1, this is premise number 2, and this is the conclusion. Oops. P1, P2, and the conclusion. We know that there is no operator under premise 2, so we will simply input the original values. And then we already know from our last argument as well that tilde b has the following values. Now, this argument is almost the same as the previous one, except now we have a tilde in front of A. So we have to calculate tilde A before we can calculate tilde dot B. So we're going to say false, false, true, true, because that's how we that's how the values are determined. The negation of the original values yields FFTT. We know that dot is true under one and only one circumstance. So we end up with the following. And then we reject each of these values, right? So true, true, false, true. Okay, now let's go ahead and eliminate the values that we don't need so that we can more clearly see as we look across each of the rows whether or not we've got a true set of premises while the conclusion is false. And yes, row number 1 yields 2 true premises. Both premises are true and the conclusion is false. This argument is invalid. Now remember, the fact that it bears out the values bear out successfully, in other words, there's no violation of validity on rows 2, 3, and 4, is not relevant. The fact that it fails at all, the fact that it fails once, means that the argument structurally is unsuccessful. The argument has to be valid on every row for the argument to be called valid and can be used as a rule for deriving lines in a proof. Okay, here we have a bit more complicated animal. Okay, yeah, that's what I want. Yeah, black. Okay. So we have 3 atomic sentences, so we have 8 rows. And we take half of the first 4 and give half of the first sentences 4 values and give those half true, half false. And then C, as the last simple statement, alternates true, false, true, false, true, false, true, false. Okay, so here is premise 1, here is premise 2, here's the conclusion. So what we can do is work forward or backward. It doesn't really matter. We're already at the conclusion, so we can start with not A. Remember, we're rejecting all of A's values. That's why instead of TTTT, FFFFF, I probably didn't count right. Anyway, we end up with alternate, the opposite values, right? 4F, 4T. And then that leaves the dot as follows. Actually, I'm going to change pen color here. Let's make it red. False, 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 and true, true, false, false. I'm going to go back to black for, actually, no, let me keep it red since we're going to be comparing premise 2 with the conclusion. So we have alternating, right? False, true, false, true, false, true, false, true, false, true, false, true. Now, for the first premise, the horseshoe is the main operator, but we need to first determine the interior of this parenthetical and then negate it. So we have false, 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 true, 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 true. You probably can see that we're going to end up with the same values as the conclusion, but let's go ahead and play these out. So we have false, 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 true, true, false, false. And then we're going to negate true, 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 false, false, true, true. And then lastly, the horseshoe. Now, if you feel like it's hard for you to remember the truth definitions for horseshoe when C seems to be on the left side of the horseshoe, but that's only the referent column, you can always put the values of C directly underneath the simple statement. But here's what we're doing. We're looking at true, horseshoe, true, true, horseshoe, false, true, horseshoe, true, true, horseshoe, false. We're looking at, where did it go? False, horseshoe, true, false, horseshoe, false, true, horseshoe, true, and true, horseshoe, false. So we need to locate all of those conclusion values with F and then look to see if the premises are true at the same time that as the conclusion is false, and that is not the case, and so the argument is valid. All right, I think we've got one or two more here. Here again, we're back to two simple statements, and so 4 rows. And I'll work backward just because these two sentences are less complicated. Remember, we've got the conclusion, premise 2, and premise 1. And I think you see that there are lines that separate the reference columns from the premises and the conclusion. Okay, so we have false, true, false, true, false, false, true, true. And then we need to determine the first tilde last, but we need to determine the interior tilde before we determine the values of the wedge. So false, false, true, 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 false, true, true, and then false, true, false, false. So we're taking only the values under the main operator. And we can see that although the conclusion is false on row 1, so also are both of the premises, and the conclusion is false on row 3, And yeah, one of the premises is true, but the first premise is false. Okay, so let us continue. Two simple statements, 4 rows, conclusion, premise 2, and then horseshoe is our main operator. So we need to determine the values for tilde b first and tilde a first. At least it doesn't matter whether you do tilde b first or tilde a first, but you have to do the tildes first. Then you can determine the horseshoe. All right, is there a row on which the conclusion is false while the premises are both true? No. And so our argument is valid. You might recognize this as a version of affirming the antecedent, also known as modus ponens. All right, I hope this practice was helpful to you. Certainly, if you have questions, let me know. And keep drilling exercises. The best way to learn this stuff is to drill, 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 and then drill some more.